Assalamualaikum and a very good morning. I'm Fatiha Ismail. I'm from Malaysian Palm Oil Board. Today I would like to present my paper presentation entitled The Effect of Chemical and High Pressure Homogenization Treatment Conditions on the Morphology of Nanocellulose. What is nanocellulose? It is a new class of nanomaterial which produced from degradation product of cellulose. Nanocellulose is a highly remarkable bio-nanomaterial which offers numerous advantages such as high surface area, high aspect ratio, high specific strength together with stiffness, environmental benefits, and of course low in cost. Nanocellulose can be prepared from any cellulose material, especially from wood pulp. Now we move to the problem statement. Due to the annual availability of oil palm biomass, especially the empty fruit bunch fiber, the use of this fiber in a value-added commodity have received great attention from the researchers and the continuous supply of the waste as resources. Second is there are very few studies that have been considered in the preparation of nanocrystalline or nanoviscous cellulose from extracted MCC by using this chemomechanical method. Instead of that, previous researchers only focused on the nanofibrillated cellulose when using this chemomechanical method. So the objective of this study is to study the effect of chemical and high-pressure homogenization treatment conditions on the morphology of nanocellulose. From the empty fruit bunch fiber, it will undergo the purification method by using the ASTM standard method to extract the EFB cellulose. The EFB cellulose will undergo the acid hydrolysis method to isolate the microcrystalline cellulose. And then the microcrystalline cellulose will undergo the mechanical treatment to isolate the nanocellulose from it. For the classification of nanocellulose by different method, first is using the chemical treatment, usually will produce the nanocrystalline cellulose, while for the mechanical treatment, usually will produce the nanofibrillated cellulose. From the literature review, there are many isolation methods of nanocellulose. In our study, we are using the high-pressure homogenization treatment combined with the acid treatment, which is acid hydrolysis. There are many potential applications of nanocellulose, such as it can be used in large screens, solar panels, car components, plane components, medicals, pharmaceutical, in cosmetic, in batteries, supercapacitors, as well as in plastic furniture. Now we move to the methodology of this paper. Starting from OPEFB cellulose, which have undergone the purification method by using ASTM standard method, the cellulose will undergo the acid hydrolysis process to produce microcrystalline cellulose at 5%, 15%, and 25% of sulfuric acid concentration. The MCC will then will be characterized by using scanning electron microscopy. After that, the MCC will undergo the HPH process at 3 different cycles, which refers starting from 0 cycle, 10, 20, and to 30 cycles. So the measurement of particle size distribution of the particle will be made by using the dynamic light scattering. The solution of nanocellulose after that will be undergo the freeze drying process, and it will be characterized by using the field emission scanning electron microscopy, FESEM. This is the schematic diagram of homogenizer. As we can see here, the size reduction of cellulose fiber can be achieved through a large pressure drop, high shear forces, turbulent flow, and also in interparticle collisions. Therefore, the extent of the cellulose fibrillation depends on the number of homogenization cycles and also on the applied pressure. So the higher the pressure, the higher the efficiency of the disruption per pass through the machine. Now we move to the results and discussion. For the OPEFB fiber, cellulose, and also for the microcrystalline cellulose. Physicochemical properties of MCC. SEM micrograph of cellulose before and after acid hydrolysis, which is MCC, have shown the raw fiber's morphology has an irregular and rough surface of fiber bundles. But after the purification method, which is ASTM standard method, it produced cellulose with uniform fibrils and smooth surface structure. While for the MCCs, the diameter of the MCC has been decreased along with the shortened length of the fibers when the concentration of sulfuric acid increased. And the smallest diameter size produced in this study for the MCC is about 8 micrometer. Now we move to nanocellulose. After undergoing the HPH process, the observation on changes of MCC derived OPEF suspension, which is at 0 cycle, to 30 cycles during the HPH process. So from 10, 20, and 30 cycles, it represents for the nanocellulose suspension. For the isolation of nanocellulose, the suspensions were passed through a high-pressure homogenizer at a constant pressure of 800 bar with passing times of 10 to 30 cycles, so that the suspension became cloudy after 10 to 30 cycles. The particles were then converted to smaller size and were less entangled. For the characterization of nanocellulose by using particle size analysis, what we can conclude here, most of the average particle sizes of MCC and nanocellulose has been decreased as the number of cycles increase. So this has indicated that the difference in acid concentrations have given different effects on size reduction. The reduction in particle diameter can be attributed to the generation of cellulose fragments as well as erosion on the surface at higher acid concentrations. Okay, this is the FISA micrograph of nanocellulose at 5% of sulfuric acid concentration. As the passing time is increased, starting from 10 cycles to 30 cycles, the nanocellulose exhibited the decreasing in dimension. It also illustrates the viscous structure of nanocellulose with mainly agglomeration. And it also involved a reduction of diameter size and also extensive deconstruction of the cell wall itself. Well, for the FISA micrograph of nanocellulose at 15% of sulfuric acid concentration, it also involved the reduction of diameter size and also extensive deconstruction of the cell wall. And there are no more fiber structure and only small rod-like shaped viscous structure in nanometer dimension were observed. While for FISA micrograph of nanocellulose at 25% of sulfuric acid concentration, there are only small significant differences among the treated nanocellulose and at different passing time, where there are no more fiber longer existed and only small rod-like shape viscous structure in nanometer dimension were observed. And the nanocellulose diameter was estimated to be below 20 nanometer. So as for conclusion, the average particle size of microcrystalline cellulose and nanocellulose has been decreased as the number of cycles increased. And then the nanocellulose was quite difficult to determine due to the agglomerated network structure, but we managed to estimate the diameter of nanocellulose to be below 20 nanometer. Therefore, the combination of sulfuric acid hydrolysis and high-pressure homogenization processes can be utilized as an effective chemomechanical process for production of nanocellulose from various cellulosic sources. With that, thank you for listening.